The fifth method in psychophysics is the preferred maximum method. In this method, a worker adjusts one parameter of the task to his or her maximum while working as hard as he can. For example, this is commonly used in material handling tasks, and in this case we set up a task, a lifting task for example, in which a worker lifts a box from a low height up to a higher height, so it's a lift. We would control the box size, we would control the start and end so that it's lifted over a certain distance. We would control the frequency, if you're lifting it once per minute or once every 30 seconds. So we would control all those, and we give the worker control over one parameter. And the most common parameter a worker would have control over within a psychophysical experiment is the weight in the box. So he would start with an unknown weight, a hidden weight at the bottom of the box, and we'd add some lead weights or weights, for example, and he'd try it. He'd be lifting, again, this box size over a certain distance at a given frequency. He would try it and decide, is it too much for my body or is it too little for my body? Could I do more? Again, we ask him to work as hard as he can without injuring his body. He might lift it a few times at that frequency and decide, I can handle a little bit more. He'll load up a little bit more and he'll try it again, try it a few more times. Might say, I can handle a little bit more, and so add a little bit more. And so finally he will settle on what he feels, what is the most weight he can handle, working as hard as he can without exposing himself to injury. Okay, so that's a psychophysical experiment that's trying to find the employee's preferred maximum. This method has been used frequently in the past to develop what are referred to as for manual material handling tasks. Most ergonomists will call them the psychophysical tables. Safety professionals probably call them either Liberty Mutual tables. I've also seen safety people call them Snook tables. But this method was used very frequently by the Liberty Mutual Ergonomics and Safety Research Center. And the gentleman researcher there was Stover Snook. And so some people call them Snook tables, some people call them Liberty Mutual tables, ergonomist psychophysical tables, but they're all talking about the same thing. It's just a database where they've tested hundreds and hundreds of workers using this method. The table that's presented in your book on page 153, they refer to it as being design goals from Liberty Mutual. And the values within this table, the recommendations are a MAL, a maximum acceptable weight of lift, or MAL. It is the most weight we'd recommend that a lifter and employee lift or handle in a task that closely matches the task in the table. Page 153 looks at lifts and lowers, but there's also a table in your textbook that looks at carries. There's a push-pull. There's even one-handed information, but that is not in your textbook. You'd have to find another source. But the goal that Liberty Mutual has set up and that Kodak is providing is to make the task acceptable for 75% of women. When they found that material handling tasks can be acceptable for 75% of women, they found that the injury rates were much decreased. So acceptable for 75% means unacceptable for 25% of women, but if it's acceptable for 75% of women, it's acceptable for almost all males lifting. On page 153, if you'll turn to that, I'll ask you to write a couple notes. Whenever you're using this table, and again, it's for a manual material handling, lifting, or lowering task, when you're using this table, the first thing you need to identify is the range of lift. And you can see this table, there's three primary sections here. Those three primary sections correspond to range. And for the range, we're going to use the natural breakpoints on your body for material handling. And those will be if you're lifting the lowest you can grasp while standing upright is your knuckle height. And so anything below your knuckle height you're going to have to bend for. The good range for lifting is typically described as being between your knuckle height up to your shoulder. It's in your, your good lifting zone. And then anything above your shoulder, you're having to use your arm muscles. You're typically weaker, and so your shoulder is another natural break point. And so in identifying where the lift primarily occurs, we're looking, does it fall from your shoulder to your reach? This will be the top part of the table. Add in that's greater than 138 centimeters. And I'm sorry, this table is metric, that's all they provide. But shoulder to reach is higher than 138 centimeters. And this is where the load is located. Your knuckle to shoulder, the KS range, is 74 to 138 centimeters. And then below your knuckle down to the floor, this will be your FK range, is less than 74 centimeters. So again, anything below your knuckle, you have to bend at your back or squat with your legs, and so this will be the low range. Okay, so that's the first thing you need to decide on a lift or lower. Second thing is the horizontal distance from the front of the body to the center of the load. Okay, so from front of the body to the center of the load. We saw in biomechanics that the further away it was, the harder it was on your back, and so the horizontal distance really comes into play there. They give you choices of 17, 25, and 38 centimeters. Okay, so three distances they've tested. Next factor to consider is the vertical distance of lift. Again, within each of these horizontal distances, they give you 3 vertical distances, and this is just how far the load has traveled vertically. Okay, so it's gone from here up to here, and so the distance, the vertical distance it's moved or traveled is there. In real life, you can measure from the bottom of the box at the starting point to the bottom when you put it down. You can measure from handle to handle. That'll be the same, or you can measure from top of box to top of box. All 3 of those will get you the same as long as you consistently measure the same point on the low part of the lift, at the beginning of the lift, and the end of the lift. And then lastly, the last factor you're going to need to define is the frequency of lift, and they measure this in 2 different units. One is 1 lift every so many time periods, so 1 lift every 30 minutes, for example, is here. The second way, it'll be on the same line, but is the number of lifts every standard time unit. And so if you lift 1 lift every 30 seconds, that means you can lift 2 per hour. Okay, so notice that's on the same line. Okay, so working through an example. Evaluate lifting a compact 20 kilogram box. The lifter handles the boxes within a 17 centimeter reach. Boxes are lifted from a height of 5 centimeters to 75 centimeters. Lifts are once every 30 minutes. Is this task within our acceptable limits? Does it meet our design goals? So on previous slide, the first thing you were looking at was the range of the lift. So range, we can see that you're lifting from a height of 5 to 75. 5 to 75 is pretty close to less than 74 centimeters. So 5 to 75 fits pretty much within the FK, the Florida knuckle range. Okay, so I'm going to go ahead and pull up that part of the table and blow it up so you can see it better on the slide. We're in the Florida knuckle range. Next thing we need to consider is the horizontal distance from the front of the body to the center of the load. And we say he's lifting within a 17 centimeter reach. 17 centimeters. So we're in this part of the table. Next thing, distance of lift. We're lifting 5 to 75 centimeters. And so the distance is 75 minus 5 is equal to 70 centimeters. That's not exactly on our table. Our choices are 25, 51, 76 centimeters, but it's pretty darn close to 76. So we're here. And then lastly, frequency, once every 30 minutes. You scan down once every so many time periods, once every 30 minutes. We're right here. And so we just look where all those things correspond, where they all match up. We can see that we recommend, as our mall, recommend 14 kilograms. And so deciding, do we have a good job or do we have a bad job right now? good job or bad job, the actual 20 kilograms is greater than our recommended 14 kilograms. That indicates the job is too stressful. There's an increased risk of injury. And so we want to redesign the job to control the hazard. And so obviously if they're lifting 20 kilograms, we want them to get it down to 14 kilograms. How can we get the load down to 14? And you would say, well, put less stuff in the box. So put less stuff in the load or lighten the container. Can you get 20 down to 14? Maybe yes, maybe no. If you can't get it down to 14 kilograms, you look at, can we change the other variables? You can reduce the distance of lift. Instead of being 70 centimeters, let's get it down to just 25. So 25 centimeters. That means you could either go from 5 up to 30, or go from 50, instead of being 5, put it at 50, 50 to 75. Okay. Notice that would only get you to 17 kilograms, still not enough to cover your actual 20 kilograms. So instead of reducing the distance of the lift, you could look at if we reduce the frequency from once every 30 minutes to once every 8 hours, that would get to 19 kilograms, which is closer. But what would really solve it is to just do it once per day. Yeah, going from 16 down to just once a day. And reducing the distance of lift on it down to 51 instead of 70 centimeters. Okay, so that combination would solve your problem. Okay, so we have an example of a lift. Kodak says that the recommendations for lowering are not much different, not significantly different from lifting, and so they want you to use the same table for lowering activities. And so if you have a lower, just go ahead and use that same page 153. For example, a job requires lowering a loaded tote 64 centimeters from overhead down to shoulder height. So overhead down to shoulder height. So we're in the SR part of the table, so shoulder to reach. Once per shift. The handles are 38 centimeters in front of the body. How heavy can we load the tote? Handles are 38 centimeters in front of the body. So our horizontal distance from the body to load is 38, so we're in this part of the table. So SR, shoulder to reach, 38 centimeter horizontal. Distance is that we're lowering it is 64. 64 falls between 51 and 76. It's not really either of those. So we'll come back to that. And then we're doing it once per shift, once per 8 hours, for example. And so we're somewhere here. The 64, coming back, the 64 is not on your table. It's kind of halfway between 51 and 76. And so we're somewhere down here. And so example could be we're somewhere in the range of 10 to 11 kilograms. If you wanted an exact number, it needs to be this in order to determine if it's a safe weight or not. You can take two approaches. One is a conservative approach. Conservative approach uses lower value. Conservative because it protects more. And so in this case, conservative approach, the answer that you would provide is 10 kilograms. Come from an engineering arena and said, well, I can get better than that. I can get a more accurate approach. I want accuracy instead of being conservative. And so an accurate example would be halfway in between those would be 10.5 kilograms. Okay. So in real life you can take either approach. You can either protect the most by giving a conservative value, or you can be more accurate from these tables. You want a numerical value. It could be 10.5 kilograms. Okay. In this solution, not much difference, half a kilogram, but in other areas you can see there might be several kilograms difference. Okay, so lift, lower. Lastly, want to talk about carry. Carry doesn't have a lifting range. Instead, it's questioning where are you holding the load. They find in industrial situations, people carry the load at about waist height, meaning with their elbows bent to 90 degrees. Or people carry with straight elbows, meaning they're carrying below their waist. And so the breakdown of the table, this top part is elbows bent, so 90-degree elbows. The bottom part of the table is elbows straight. Okay, so with their arms extended. It has second consideration, second factor you need to consider is the distance of carry, and it gives you 2.1 up to 8.5 meters, again metric meters. And then lastly, the same frequency as in the previous table. And so for an example of carry, say you lived on campus, you go to Winslow Cafeteria for your meals, breakfast, lunch, and dinner. How much food can you put on your tray and be able to carry it 4 meters to your table? So how much food can you put on your food tray at Winslow Cafeteria and allow you to carry it back to the table? And so first question is, as you watch people carry food trays, walk with food trays as they've just loaded up with food they're going to eat, do they carry it with their elbows bent or with their arms extended, meaning their elbows straight down? And you're going to find that people carry it with their elbows bent. I guess they want the food close to their mouth, so elbows bent. My example, they're carrying it 4 meters. 4 meters is pretty close to, darn close to 4.3 meters. And then frequency, if they eat 3 meals per day in the cafeteria, it's a little bit more frequent than once every 8 hours, but this will be your closest answer. And so the answer for this is 21 kilograms is your recommendation. 21 kilograms. Multiply that if you want to know how much in pounds that is. There's 2.2 pounds per kilogram. And so that will equal 40, let me find my notes here, 46 pounds. 46 pounds of food. Okay, so with that, I want to go ahead and stop this.